Number 1. Why does the domain differ for different functions? Well, if you substitute some values in the variable of certain functions, you could get something undefined. For example, if you have f of x equals 1 over x, if you let x equal 0, then you have 1 over 0, which is undefined. So 0 is not in the domain of this function. You could have another function, for example, g of x is the square root of x. If you let x be a negative number, then what you would get is an imaginary result. So for example, the square root of, let's say, negative 9. Oops, let me make that negative 9 in there. Well, in the real numbers, there's no solution for this. There's no real number answer because a number times itself will never equal a negative number. And because, well, take negative 3. Negative 3 times negative 3 equals positive 9. 3 times 3 equals positive 9. So no real number will work here. Of course, the answer in the complex number system is plus or minus 3i, where I squared equals negative 1. That's an imaginary number. All right? But that's not in the real number set. So we're working with real numbers so far, so there's no solution for that. So negative numbers are not in the domain of this square root function. Number 3. Explain why the domain of f of x equals cube root of x is different from the domain of f of x equals square root of x. Well, you can take a cube root of any real number. For example, cube root of negative 8. That's equal to negative 2. Because negative 2 times negative 2 times negative 2 equals, this is positive 4 times negative 2, which is negative 8. So this will work. The cube root function will handle any real number, positive or negative. There is no such domain for the square root function, though. Alright, we talked about this in problem number 1. We have, for example, the square root of negative 9. There's no number which, multiplied by itself, equals negative 9. The problem is that negative sign. When you multiply a number by itself, even if that number is negative, you're going to get a positive result, or you could have 0 if x equals 0. But you're not going to get a negative result. So that's why the domains are different for these two functions. Okay, so the domain of the cube root of x is the whole real number set, or negative infinity to infinity. And the domain of the square root function is everything from 0 to positive infinity, including 0. So here's a half open interval there. Okay, number 5. How do you graph a piecewise function? Well, you just graph each function separately using only the values in each given domain. So one way to do it in a practical way is you draw your axes. And we'll practice this more later when we actually do some piecewise graphs. But if you have domains separating the XY plane like this, let's say you've got three different domains here, you can, let's say you have a line in this domain and maybe some kind of curve in this domain. All right, you draw your line. If you need to, you can extend this line, but just draw it in dashed. So for example, if you want the y-intercept, you can draw it so it hits the y-axis, but use a dashed line when it goes out of its domain. And then you can erase that dashed part. Okay, so it helps if you use a pencil on this one, or doing these kinds of graphs. You would erase that part once you've got the line drawn. And if you need to, if you're really into being neat, you can use a little tool from drafting called an eraser shield. You can use that with your pencil and an eraser, and you put this eraser shield over the part you want to erase, and it'll cover the stuff that you don't want to erase. Okay, this is an old drafting tool that I used in high school when I took drafting. This was way before computer-aided drafting, so we did everything by hand. It's lasts a long time. It's a piece of aluminum, and I think you can still get these. So that's what I used. I used a drafting shield, and you may not want to go to all that trouble, but you know, this is kind of a mess here because this doesn't erase well. But you can draw your other curve in like that, and then whatever is over here. All right, but you can draw them in completely and then erase what you don't want that extends into the other domains. So that's a practical way to go about it. Okay, number 7. It says, for the following axes, find the domain of each function using interval notation. Let's see, we've got f of x equals 5 minus 2x squared. Or, if you prefer, negative 2x squared plus 5, which is equivalent. So this is our familiar quadratic function. It's a parabola that opens downwards. I know it opens downward because the leading coefficient, which is next to the x squared, is negative. If it were positive, it would open upward. All right. It is a polynomial function as well. It's a polynomial, as you can see, and all polynomial functions have domain in the real numbers, all real numbers. So the domain is negative infinity to infinity. No real number will make that undefined. So everything works in this one. Number 9. F of x is 3 minus the square root of 6 minus 2x. Alright, when we talk about the square root function, we said you can't take the square root of a negative number because you'll end up with an imaginary answer, a number that's not in the real number system. So it's undefined in the real numbers when you have negative numbers. So we have to make sure that this radicand, all the whole expression under the radical, is not negative. So another way of putting it is we have to say 6 minus 2x must be greater than or equal to 0. Alright, that's another way of saying it's non-negative. It must be 0 or greater. And then this would be the domain of this function. So what we do is we solve this for x. We move the negative 2x to the other side, change the sign, or add 2x to both sides. And then we divide both sides by 2. So 6 divided by 2 is 3. And 2x divided by 2 is x. So, in other words, x is less than or equal to 3. And that's our domain. Everything less than or equal to 3. So writing this as an interval, we've got negative infinity to 3. And we are including 3 in that, so we put brackets on the right side. So that's everything from negative infinity to 3. So remember, whenever you use this interval notation, use parentheses next to infinity or negative infinity, because infinity or negative infinity are not real numbers. They're not numbers, all right? So that's not included in this interval, so you put the parentheses next to it. Okay, number 11. We have f of x is square root of x squared plus 4. So the radicand of a square root cannot be negative or less than 0. So to get the domain, set this radicand, the expression that's under the radical, in other words, greater than or equal to 0. And then solve for x. So we have x squared is greater than or equal to negative 4. Now, whenever you square a real number, you're never going to get a negative result. So this expression here can be satisfied by any real number, all right? So you need not go any further than this, okay? X squared, no matter what x is, when you square it, you're always going to get something greater than or equal to 0. So any real number will make this true. So the domain is all real numbers, okay? Negative infinity to infinity written as an interval. Again, remember to use parentheses next to the infinity symbols because those are not real numbers there. So you're not including those. Okay, number 13. F of x is the cube root of x minus 1. So, a cube root is defined for all real numbers, all right? So certainly x minus 1, no matter what x is, will be defined when you take the cube root of that. So anything will work here. There's no need to solve anything here. You just think it through. And the domain is all real numbers, negative infinity to infinity. Yeah, you can take cube roots of positives, negatives, whatever. All right. Okay, number 15. We have f of x is a rational function. In other words, it looks like a fraction here. A rational number is a fraction, so a rational function is also in fraction form involving variables. So we have f of x is 3x plus 1 over 4x plus 2. Now, anytime you're dealing with fractions, the problems come in when the denominator is equal to 0. That's the only time you're going to have any difficulties with a rational function, when the denominator equals 0. So we have to make sure that anything that makes that denominator 0 is not in the domain. Otherwise we get division by 0, which is undefined. So what we do is we set the denominator, you could set it equal to 0, or you could do it like this if you wish. It cannot equal 0, so I put the does not equal sign. And then I solve this for x. Let me subtract 2 from both sides, or move this to the other side. Divide both sides by 4. Negative 2/4, that's 1/2. Negative 1/2. Another way to do it would be to set it equal to 0, solve for x. For x plus 2 equals 0, and then solve that for x, you get x equals negative 1/2. But just understand that that's not going to be in the domain, because that'll make your denominator equal to 0. So written as an interval, this goes from negative infinity to negative 1/2, but not including negative 1/2. So you put a parenthesis next to it, and the union of that with, again, another parenthesis, you're not including negative 1/2, to infinity. So basically, if you graph this on a number line, that's going toward infinity and that's going toward negative infinity. You're not including the point negative 1/2. I'll put an open circle around that, where you're including everything else to the right and to the left on the number line. All right.